When we talk about digital speed, we usually think about data download capacity. But the real enemy is a hidden wait time known as latency. If you play fast-paced online games, you've experienced this directly. You press a button to fire or dodge, but that action takes a fraction of a second too long to reach the server. By the time it registers, your character is already gone. That microscopic delay dictates the difference between a win and a loss. In the macroeconomy, this delay is even more punishing. In high-frequency financial trading, algorithms execute orders across the globe in fractions of a millisecond. A single millisecond of latency can cause an algorithm to miss a price fluctuation, resulting in massive financial losses before a human trader even blinks. As our digital networks handle increasingly critical, time-sensitive tasks, latency has become a fundamental structural risk. It's tempting to think that upgrading to a faster gigabit internet plan solves this problem. But having infinite capacity does not actually cure data delay. Think of bandwidth as a multi-lane highway representing maximum network capacity. Throughput is the actual achieved traffic rate. During a jam, the volume of cars drops significantly. Finally, latency is the round-trip time for one specific car to reach the destination and return. Upgrading your network bandwidth increases the sheer volume of data you can send. But latency is the inescapable physical time it takes for any of those individual packets to actually arrive. Latency is the total sum of 4 distinct physical and processing hurdles. First is propagation delay. This is the raw physical time required for signals to travel through a medium. Even though a data pulse moves through fiber optic cables at about 2/3 the speed of light in a vacuum, a cross-country trip still takes dozens of milliseconds, simply because of the sheer geographical distance. Next is transmission delay. This is the time it takes for your hardware to push the data packets onto the wire in the first place, a rate constrained entirely by your local link's bandwidth. Third is processing delay. Every time data passes through a router or a load balancer, that machine has to inspect the packet, read its header, and determine its next routing path. Finally, there is queuing delay. When network traffic is highly congested, packets are forced to sit in hardware buffers, waiting for their turn to be processed. Because network latency is compounded by absolute physical distance, hardware processing time, and traffic jams, you cannot solve it simply by paying your internet provider for a higher capacity connection. When engineers measure these delays, looking at the average response time gives a false picture. To understand true user experience, you have to look at tail latency. This chart plots out a typical distribution of network response times. The massive spike on the left shows a fast average latency of 10 milliseconds. But if you look far to the right, you find the P99 latency, the 99th percentile, at 500 milliseconds. 1% sounds tiny, but out of 1 million daily requests, that tail means 10,000 users experience severe lag. In system design, average metrics provide a false sense of security. The tail latency reveals the actual breaking points of the network. These breaking points are becoming critical because we are moving toward the tactile internet, an era where machines require real-time, synchronous visual and haptic feedback to function. Human perception is highly sensitive to timing. For an operator to feel like they are directly interacting with a physical object through a screen, the round-trip network time must stay under 10 milliseconds. Anything slower causes severe cognitive dissonance. This strict millisecond requirement applies to critical physical fields. In remote-controlled robotic telesurgery, a doctor manipulating controls miles away needs immediate haptic resistance from the tissue they are operating on. A slight lag means cutting too deep. To operate safely, medical and industrial systems require networks that maintain this sub-10 millisecond threshold consistently. Since we cannot break the speed of light, engineers have to bypass it. The primary solution is edge computing. Instead of sending data across a continent, servers are pushed to the absolute edge of the network, physically shrinking the distance the data must travel to reach the user. By caching data locally on neighborhood cell towers and regional hubs, networks eliminate the need to route everyday requests through massive global infrastructure, like transoceanic cables resting on the seafloor. We simply cannot make data travel faster through the wire. So, the ultimate goal of modern network engineering is to build the systems so physically close to us that the wait times simply